Hello everyone, thank you for joining us today for our in situ fracturing analysis using the high resolution injection tool for design optimization of sodium permanganate injection webinar, presented by our guest speaker, Mr. Scott Wisher. I am Laura Robeson for Caris Corporation. A few items to cover before we get started today. Today's webinar is being recorded and will be available on demand after the live session. All attendees will receive a follow-up email after the webinar with the link to access the presentation. We encourage you to share this within your organization and network. If you are interested in receiving a PDF of today's presentation, please contact us directly. To ensure the best audio quality, we have everyone in listen-only mode. If you have questions, we encourage you to submit those throughout the presentation using the question pane in the GoToWebinar panel. We will be taking questions at the end as time permits. Here is a quick look at our 2017 webinars through May. February 23rd, we will host Safety and Handling of Permanganate with Mr. John Bull, our Global Technical Program Manager. On March 9th, Mr. Darren Scott, Technical Service Manager, will present Safety and Handling of Phosphates. April 27th, we will host Polyphosphates for Metal Immobilization with speaker Dr. Pamela Dugan, Business Development Program Manager. And on June 1st, we will host ISGS, a modernized stabilization technology for DNAPL. To register, please visit our website. The recordings of each webinar are available on our website at cariscorporation.com. Here are a few ways to find us. Visit our website at cariscorporation.com for product and technical information, webinar links, webinar schedules, and more. Listed are the general sales and marketing email addresses as well as mine. Follow us. We are on LinkedIn, YouTube, Google+, Facebook, and Twitter, where we frequently post technical articles, upcoming events we are attending, webinar schedules, as well as recordings, and much more. At this time, I would like to take this opportunity to introduce our speaker, Mr. Scott Wisher. Mr. Wisher is a professional geologist and has over 15 years of project and business management experience in the consulting and field services industry in the Rocky Mountain region. He currently manages the Midwest region for Cascade Technical Services and oversees technical staff implementing remediation and characterization projects from the Denver, Colorado, Houston, Texas operational centers. Mr. Wisher's expertise is in remediation system design using chemical remediation, mechanical remediation, effective utilization of high-resolution site characterization for remediation design, plus profit and loss management to support business operations. Mr. Wisher has presented at multiple conferences throughout the country on remediation and characterization services and serves as a project technical lead for Cascade. Please welcome Mr. Scott Wisher.
All right, thank you, Laura. Really appreciate this opportunity to be with you all today. We've got a lot of attendees, so I greatly appreciate everybody joining along. To give a little just additional introduction to myself, like Laura said, I sit in Golden, Colorado, but I'm the Midwest Regional Manager for Cascade. And I was consulting at the early part of my career as a remediation manager for a firm here in Denver, and then I was with Vironics for about 5 years prior to our acquisition by Cascade a little over 2 years ago. So what I'm going to be talking about today is evaluation of injection services and evaluation of implementation optimization, if you will, to evaluate how we can optimize at the pilot scale to scale up to full scale. And the way we have done this is through the use of the high resolution injection tool. And for our talk today, we're going to be talking about a full-scale sodium permanganate project that we worked on in Little Rock, Arkansas. So I really, for those of you that have seen me present at conferences before, I do my best to not read slides verbatim because that's terrible for me and terrible for you as well. So I promise this will be the only time I'm going to read verbatim, but I think this is a really important point when we think about success factors for distribution of amendments. A lot of us on this call, we've done injections. We've had probably many of them go well. We've probably had many of them not go so well. So we want to really think about why that happens. So to effectively degrade contaminants, the oxidant must come in contact with the contaminant molecules. Ideally, the delivery technique would ensure that the oxidant is evenly dispersed throughout the area to be treated. It's a really interesting saying by ITRC. This came out about 12 years ago. So let's think about this. In order to effectively degrade contaminants, we must come in contact. That's something that we all think about, and I think we all know, especially when it comes to in situ chemical oxidation. But do we really know how to manage it and how to affirm that that's happening, confirm that we're doing it with our injection strategy? And then the oxidant has to be evenly dispersed throughout the area to be treated. It means we need good distribution, and that will also equate to putting more oxidant in areas where there's more contaminant and less oxidant in areas where there's less contaminant. So that'll be the only thing I read for you guys verbatim today. But now let's talk a little bit about the project that we were working on in Little Rock, Arkansas. And so we were tasked with an ISCO sodium permanganate project with a former manufacturing facility. And we knew that we were going to use sodium permanganate just based on the chlorinated solvents at the site and the history of the site using solvents. But what we wanted to utilize was, because it was such a large area, we wanted to utilize the HRIT, which is what we call the high resolution injection tool. And I'll run through exactly how that HRIT works and why it works and how we utilize it for full-scale implementation. And so what we wanted to do was utilize the HRIT to evaluate both a direct push injection strategy and a well injection strategy. I'm sure many people on this call have done a lot of direct push injections, and then there's also a lot of soluble reagents that are applicable to injecting via wells. Okay, so I want to give you a look of what this tool looks like, and then we'll really dive into how it works. This is how we implement it in the field. It's a large tank of water, followed by a system that we built, which includes a hydrocell pump, which is the picture on the right. The pump is just below that, and you can see the flow meter, some pressure gauges, both on the up gradient side of the pump and then on the effluent side of the pump as well. And then just the middle picture is some of our data analysis as we're using the tool, evaluating nearby monitoring wells. So let me show you a little P&ID of kind of how this works. Water tank, which I just showed you, positive displacement, hydrocell pump, moving outwards towards some pressure relief valves with a recirculation system. I think that's really critical both in full scale and in pilot scale to have a recirculation system to evaluate or be able to control better your pressures and flows. Pressure transducer followed by a flow meter, and then you move into your actual tool that goes into the ground where you've got another down gradient or downhole pressure transducer. This is all monitored in real time with data collection software, which is output through Microsoft Excel. I'm going to show you a lot of those data outputs today. So here's the general steps of how this process works. We know for any given site, based on other data, soil analytical data, groundwater analytical data, other high-risk characterization tools that may have been used out there, sort of the general area in which we're going to be injecting, or where the contamination lies, I should say. So for the use of the HRIT tool, we typically push it to the target depth, and again, it's a direct push tool, and we'll push it to the target interval, and what we then do is begin that hydrocell pump and engaging that pump at roughly 3 to 5 psi increments until flow is achieved. Of course, there's a little bit of compaction pressure around that direct push tool. We need to get through that. But in general, what we're looking for is a linear relationship between pressure and flow. As we send flow out and pressure increases, we then get a resultant flow. Of course, we then continue increasing pressure until interval is either fractured, which I'll show you sort of what that looks like in table form here in a second, or our optimal flow rate is achieved for any particular project. We evaluate those data at that interval, and then we can push or pull into the next interval and start the process again. Okay, so this is a general slide that I wanted to show you, not necessarily for the project we worked on, but this is something that your injection subcontractor should be able to provide to you with any given project, especially with ISCO, because of that ITRC document or ITRC saying, which said you must achieve contact for this to work. And so fracturing in ISCO can be a challenge because unless it's a long-lasting ISCO product, then if you don't get that direct contact, you're not going to get the oxidation that you need. So this is a general slide where, as you can see over time, we're ramping up pressure, and then what you see is at about 150 psi, you get a major breakthrough and a major loss in pressure, followed by a resultant flow, which is shown in red here. This is what we would call emplacement or hydraulic fracturing of the system, so that we created a small fissure, which was then filled with water or some reagent. This is typically the type of slide I would like to see with respect to pressure and flow. It implies that as we ramp up pressure, we are seeing a resultant flow, and we would call this more plug flow. You're just filling up pore volume as you're pushing water or reagent into the lithology. Okay, so let's talk about the actual tool at this site in Little Rock. But first we'll talk a little bit about why it's important and why it was important at this particular site. So of course we want to evaluate pressure and flow for the direct push area of the site that we knew was going to be direct push, and then an area that we believe was going to be used with well injections. And so we wanted to be able to use the HRIT to optimize the flow rates and the pressures that would be used at the full scale, so that we could really understand how long we were going to be in the field, at what limitations we had, both with pressures and pumps needed, and the time it was going to require to be in the field. The thing that I probably love the most about the HRIT tool is that we can inject at design volumes. If we know the stoichiometric demand for some reagent is X gallons, we can inject that number of gallons through the HRIT tool. For many, many years I've used the hydraulic profiling tool, and I like that tool. I like the data I get from it. One of the challenges I've faced is that it can be harder to scale up to the design volumes that will relate to your full-scale design. The other thing that we're seeing in many states as we're injecting is regulators concerned with fracturing. We're talking about fracturing here, and so regulators have a lot of questions. Nebraska probably being the one that is most that I work with the most, where they have a 1 foot per foot of overburden PSI regulation. And so that's a challenge when you can't put in anything at 50 feet at over 50 PSI. And despite the fact that you can present to them information with respect to how the fracture is being created, they've still got this kind of blanket rule that we're trying to work around. So if you're working in one of those states, this is a way for you to demonstrate that you aren't going to fracture. And if you are going to fracture, which is sort of point 4 here, you have the backup data to demonstrate the need to remediate. This product has to get in the ground in some way, so we need to figure out the best way to work with both your clients, my clients, the regulators in order to get this material in the ground. Okay, so how's it deployed? I kind of showed you the drawing and the diagram. So it has a direct push tool. It's got an integrated uphole and downhole pressure meter or pressure transducer, and then a flow meter. Got that hydrocell PD pump with the recirculation system, and that really allows us to provide a consistent flow and ability to dial in our flow rates. Gives us a real-time data analysis through Excel. I think my next slide has some of our data outputs that I'll start walking you through. And then, of course, we can not only use the HRIT tool, we can use secondary and tertiary methods of monitoring effectiveness, ROI, and distribution through EC profiling or DPT coring if you have an amendment like permanganate, which would be obviously purple. And then there's other indirect well parameters, which I'm going to show you a little bit today as well. Okay, so here's the cross-section that we were given at the initiation of this project. And we knew that the target was what was called a shallow sand. And that was seen pretty consistent across the site. And I pointed out, because it's noted as shallow sand, but as I really dove into this, even at a site where at a macro level it is a shallow sand, if you dive in, you really start seeing a lot of MLs and SMs, a lot of silty material. And so when you have those, that very silty material or some silts with a coarser grain material, obviously your distribution is going to be it's not a sandbox, that's for sure. Okay, so we really wanted to optimize delivery of permanganate. That was the selected remedy at this site, and we wanted to figure out the best way to manage that. So first thing I said today was contact is really the king here, and fracturing is really best applied in tight soils. Many of us have done zero-valent iron and some of the slurry-based materials. The goal of those is to fracture and place them into the system. I don't believe that that's the optimized way to handle permanganate because of the contact. So in order to optimize, we wanted to use the HRIT with 3 injection styles that can be measured with the tool. So I've already mentioned them to you. Here's what they look like. We're doing a traditional PVC well. These were already in place when we got to the site. So just a 2-inch monitoring well with a 10-foot screen. A direct push micro well, so that's just installed with direct push, 1-inch well with 10-foot screen again, and completed just like a normal well. And then of course the direct push injection with a 2-foot screen. Okay, so here's the site map at least. And what we're going to do is evaluate the DPT versus the injection well, so we can evaluate the full scale permanganate. All right, so let's dive in. I'll zoom in a little bit on that map and just give you, we're only working in one tiny area of a very, very large site to deploy the high resolution injection tool. And what we did was go near 2 monitoring wells 21 and 23. And we did two direct push points near each of those, plus 1 injection point. Those were those micro wells that I mentioned to you a few minutes ago. All right, so this is your first look at what the data output looks like from the HRIT. And this really is what we want. And so this is actually from the site. This is DP1 from 14 to 16 feet. And so let me introduce, it's the first time you've seen this. The red is flow, blue is uphole pressure, and then on the left y-axis, of course, is flow, right axis is uphole pressure, and then of course we've got time on the x-axis. So this really is what we want, like I said. As we got to roughly 1132, and we started ramping up pressure, we saw a resultant flow. And it was very stepwise, right in line with as we increased pressure, we got a linear relationship with flow. Let me show you the opposite of that, which happened at another hole, which happened a little bit deeper. So this is DP4, and this is from 18 to 20 feet. As you see, as we ramped up pressure in the blue line over time, we're not seeing any flow or very, very little flow, less than 1 GPM, until we reached about 80 PSI. And all of a sudden we get that fracture pressure that I showed you, or that fracture that I showed you on that one of the first slides. And of course, as soon as we see that fracture break through, we see a resultant flow. And so this is uncontrolled flow, or what I would call uncontrolled flow into your system. And so this gave us a lot of great data on the pressures that the system could take at that depth and help us sort of evaluate and design for the full scale, understanding that at this depth, this is something we need to be managing. Okay, so I'm going to take you through each of the 3 systems. We did the DPT, like I said, we did the 1-inch wells, and we did the 2-inch monitoring wells. So here's direct push 1, 10 to 12 feet. And I'll run through all 3 of them here, 14 to 16 and then 18 to 20. Ultimately, at all 3 of these locations in DP1, we saw a generally linear relationship between flow and pressure. As we ramped up pressure, we saw that relationship to flow. So this was exactly what we wanted to see. And what we were able to achieve was about 7 gallons per minute injection at 50 PSI. And so we were comfortable with that as far as the full scale, and we use that as our baseline moving forward. So let's look a little bit at the temporary wells. So these would be those 1-inch wells that were installed with direct push. Again, 10 to 20 feet. These are 10-foot wells. These are a little bit different, much larger screened interval than the direct push version. Overall, at IP1, IP2, and IP3, we had that same resultant between pressure and flow. As we gave it pressure, it achieved flow, and we didn't fracture. We never saw that breakthrough. So the flow was generally linear with pressure up to 7 GPM, just like it was for the direct push. However, what we noticed was that we were able to achieve 7 GPM at 30 PSI. And this was not an accident that we held things at 30 PSI. One of our bigger challenges with well injections, especially in heterogeneous materials, is keeping pressure low. The last thing we want to do is put too much pressure on a well and compromise it by blowing out the well annular material. So here's the permanent wells. Once again, we saw roughly 7 GPM was able to be achieved at 25 PSI. And again, these are 10-foot well screens across these 2 monitoring wells that were in the area. All right, so this is a well, or this is another, I mentioned you secondary and tertiary ways of evaluating how your distribution is going. And we utilize this with the HRIT tool. This slide I actually took from Weston. I didn't mention them at the beginning, but this is a Weston project. I've been working with them for a very long time on this. And so they were doing some secondary analysis of nearby wells as we were doing the injection. These 2 slides I really love. So the one on the left here is hydraulic head monitoring. As we were injecting into DP1, they were taking nearby wells and, of course, just using a water level meter to evaluate changes in head, so groundwater levels. And that was a very easy thing to monitor and track. Of course, as you're putting water into the system, many of us have seen this before, you will get a resultant pressure down, downgrading in some direction where you'll get a resultant increase in groundwater levels. So I think that's great data. It doesn't necessarily mean that you're getting radius of influence all the way out there, but it does imply that you are influencing the system in some way. The one well on the right, or the one slide on the right here, is a way to evaluate actual radius of influence. I really love this slide. I'd never seen anybody do this before. Because it was very, very cold and we were doing this in the middle of winter in Little Rock, Arkansas, it was very easy to have a warm set of water we had just gotten from a hydrant, which of course was warmer than the groundwater. And so what we did, or what Weston did, was actually measure the temperature of water. We knew the temperature of the hydrant water. We generally knew the temperature of the groundwater. What you could do is actually measure the flux almost of the injected hydrant water coming through your system. This not only implies not just that pressure change, but actually the water of your injection making it to your groundwater monitoring well. And so this is a really great way, just another piece of data to help you evaluate ROI and what you're going to achieve at the full scale. Okay, so this is your first dive into the site, if you will. There's 2 areas, what we call at this site. There's the source area, which you're looking at here, which is generally on the south side of the facility. This is the area, due to higher concentrations in the groundwater, that the selection was to do direct push across this entire area. And so this is the area in which we did the direct push HRIT data. And so using those data from HRIT, we sized it to this full scale. And as you can see, there's many, many injection points across this map. And we were doing 2-foot intervals, just like we did during the HRIT test, from 10 to 20 feet roughly. And we felt like we had a really solid understanding of the formation's ability to accept sodium permanganate. So here's what the system looks like in full scale as we actually implemented. We were doing upwards of 5 points at a time, each with their own flow meters, so we can kind of keep within the factors and the understanding of what we wanted based on the pilot scale. And here's the site. This is right next to Little Rock Airport in Little Rock, Arkansas. And so this is just one of the parking lots, one of the injection locations. Like I said, we were doing upwards of 4 to 5 at a time. Okay, so our goal here, of course, was to inject the stoichiometric need that had been calculated for sodium permanganate. So based on the TCE and other chlorinated concentrations, Weston designed a 20% sodium permanganate solution, roughly 210 gallons per point at those 2-foot intervals. And depending on in which area, we either doing 8 to 18 feet or 10 to 20 feet below ground surface. So a spacing of 10 feet, which equals, of course, an ROI of 5 feet. And that included injection and then the groundwater transport. Of course, we know K, we know seepage velocity, and so we can we can fill up a large pore volume over time, even though you're not filling it up with the direct injection. So the HRIT data that we collected a few months prior was really gave us a sufficient base knowledge to understand what it was going to look like at the full-scale implementation. A few exceptions that we did note. So we had no surfacing during the HRIT, and we started thinking about why we were now seeing a small amount of surfacing in the actual full-scale injection. Some of the things that we considered were perhaps we should have done the HRIT in multiple areas. As I noted on that one small map, you saw where we did the HRIT, and we did that in a very small select area, and we made some assumptions that we had some homogeneity across the entire site. I think we probably found out that that wasn't quite true. So in future events, we've been much more dynamic in where we've done this so that we can get a little bit more variability across the site. Of course, you have kinetics of permanganate compared to water. And the kinetics of permanganate are not that high compared to some other oxidants, but there obviously are reactions happening here. So perhaps there was some reactions happening with the lithology that were not present during the water injection. And then, of course, we think there could have been an increase in fines in select areas. And so when we placed our injection screens at those intervals, it was less permeable than what we had seen during the pilot scale. Now, of course, we wanted to, the great thing about permanganate, one of the great things about it is that it's so visible, and we can evaluate distribution with visual cues as well. And so here's one example. Near injection point 74, we did inject all 210 gallons of the design from 15 to 17 feet. Everything went according to plan. Flow and pressures were within the HRIT established range. We measured no fracturing. We didn't have that breakthrough. The interesting thing was that we noted permanganate in a boring about 3 feet away at 18 to 20 feet, and that was immediately after the injection. So this really did meet our expectations for flow and pressure, but the interval was unexpected. So that's something that we've thought more about and led us to evaluate, did we have some changes, small changes in lithology that we weren't anticipating. Okay, so here I want to show you the downgrade. This is a downgrading area in blue. This is just to the north and northeast of that large pink section you just saw. This is an area for where wells, because it was anticipated, like all ISCO events, multiple injection events, especially in the downgrading area. And based on the HRIT, as I showed you a few minutes ago, we evaluated it at 7 GPM at less than 30 PSI. And of course, that's to both meet our timing needs, but also keep it below the pressure which would potentially compromise our wells. 20-foot spacing and 10-foot screened interval from 10 to 20 feet. All right, so this is the well injection. We had put these wells in a couple of weeks before. Again, these are just 1-inch wells put in with 4-inch casing, so not a very large annular space. So after we used the HRIT and we began this injection, we started thinking about what was working and what wasn't. So again, lower concentrations in the downgrading area, and the need for multiple injection events was anticipated during the design phase. So here we were injecting roughly 1,300 gallons of 10% sodium permanganate, so lower concentration permanganate across that same interval, that same 10-foot screened interval. And then the ROI of 10 feet for a 20-foot spacing. That, again, just like last time, that included both the volume that we're putting in and then groundwater transport over time. So some of the challenges we faced, we felt like we had a great base level understanding of what was going to happen. Some of the challenges we did see during this event was the fact we didn't see surfacing. I mentioned that before, but we did during the well injection portion of this. It wasn't at every well, maybe at 5% of the well, so a small portion. The thing that HRIT didn't do during the pilot scale was evaluate distribution inside the well, if you will. We've got a 10-foot screen. We don't really know where water inside that 10-foot screen is going. And so, we just know that it took water, and it took it at these flow rates and at these pressures, but unfortunately we weren't able to really evaluate where that water was going. And so what we found during the full scale, when we actually were putting permanganate into the ground, was distribution across such a large screen was not even. it was really taking it into coarser grain materials. The finer grain materials were not as accepting of the material. So here I'll give you one example of what this looked like on the implementation side. So near injection well 24, we put in all 1,300 gallons of the 10% solution from 10 to 20 feet, and then we did borings nearby. Everything was matched inside the parameters set forth by the HRIT tool. We measured no fracturing inside this well. So we did note permanganate in a boring from 19 to 20 feet at about 3 feet away, and that was immediately after injection. So again, this implies that we got permanganate in, but it just did not distribute evenly across this 10-foot screen, and I think that implies a little heterogeneity across the system. So of course we wanted to look in other areas for oxidant distribution and just come up with some general guidelines of how successful this was versus other areas. So we collected a lot of soil cores between injection points, and for the direct push areas, it showed good lateral and vertical distribution of permanganate in the source areas. And remember, the source areas is where we did the direct push of locations. Less so in the downgradient areas. So in the well areas, our distribution was not as consistent. One of the positives is that permanganate monitoring, post-injection has shown that there's still a lot of permanganate in the system. And of course, it's got good persistence, one of the best factors or properties of permanganate. It's a very long-lasting oxidant. And so we've still got a lot of permanganate in the system over a year since our injection event. So of course, everyone wants to look at results, and I think these are very important. I don't think they tell the whole story, but I think they are something that obviously we're continuing to consider. So you can see there wasn't a lot of injection or a lot of sampling events pre-injection. You can see our ISCO injection roughly November to December of 2015. In pre-injection, we had 4 wells that were above what would be considered the TCE cleanup goal for this particular site. At the completion, at the most recent sampling event, which was just about 5-6 weeks ago, we have 3 wells that are now below the remediation goal. So I want to kind of run through those and why we believe some of them have gone up, some of them have gone down, and we'll talk about some of the factors on why that is. So first, we'll start with these 3 wells, the ones that are all now below our remediation guideline. So as you can see, I put 3 black circles on this picture about where those particular wells are located to give you a better feel. And I think there's a few reasons why we can claim, initial success with pulling down concentrations. And I think a lot of it has to do, we put a lot of reagent, especially in the pink source area, we put a lot of material into the ground with a very tight spacing. We knew that we're getting lots of good and lateral distribution based on our soil cores. So I think that's the reason that we've seen such good results. When Weston has been out monitoring these 2 wells in particular lately, they're still getting a lot of purple, and they're monitoring light purple to purple to dark purple in all the on-site wells to really track the oxidant breakdown and demand. And then on that one on the north side, in the downgrading area, if you can imagine that you've put in 1,300 gallons in each of those points, which is up gradient of that point. So there's been a lot of groundwater flow that's come through there in the last year, and a lot of upgrading permanganate that's moved through that system. So I think we've seen some great results there for that reason. All right, so let's move back to these 2 wells here. Now, you can see pre-injection back in roughly 2014, about 2 years ago, we were just slightly below, one of them was slightly below the remediation goal, still had TCE in it. But then 2 injection events, or 2 sampling events post-injection, we've seen a really significant increase in TCE. The great thing is, in this last sampling event a few weeks ago, we started seeing a decrease in concentration. So hopefully this is the beginning of that breakdown to really kind of get going, and this is a trend back downward. So let me show you where these are. This might surprise you. So you can see my blue circles where I put those. Those are outside of the injection area. And I think talking to some folks at Weston and thinking about this, based on the volume we put in, where we put it in, I think there's a chance that in the very short term, we probably mounded a little bit of TCE, moved it down gradient, and it's now been showing up in monitoring wells 20 and 21. I think many of us in the injection industry and business we've seen this before, typically a very short-lived type of thing. When you put such a hydraulic head on your system, you'll have a tendency to, in the very short term, mobilize things. So I'll be really interested to see when the March data comes out, kind of how those wells are progressing. So I want to wrap it up here by talking about our results and then modifications that we've done and are doing to the HRIT system so that we can, forever make it better every time we take it out. So the HRIT at this site really did provide a great baseline knowledge of achievable pressures and flows for a very large site. It gave us our pressure and flow ceilings, and that's something we could provide to our field staff and our design staff for implementing and knowing how long any particular project or how long a project was going to take. This is roughly a $30,000 project, with the full scale at being about $350,000. So I think, to spend less than 10% on the design optimization and using the high resolution injection tool is a pretty valuable way of really dialing in how efficient you're going to be, what your pressures and flows are going to be, so that you can maximize your likelihood of success in the field. I think one thing that we have done and could have done at this site was implement at more locations across a larger site, and that would really account for some of the variability across the site in lithology. The HRIT in wells really did provide a great understanding of flow and pressure characteristics, but like I mentioned, we didn't really have a great feel for where inside that well it was going. I think wells with a shorter screen would perhaps be more efficient use in the future so that we could really understand where that material was going. There's some other modifications that you could do. High resolution injection tool could use it with a tracer dye. If you're not using reagent, you could be using some type of yellow dye and then do coring to try to find it. And you could do that around wells, around DPT points. Of course, if you're using a soluble amendment, anything that would show up on an electrical conductivity, if you can push that tooling into the ground, that would be another way to evaluate distribution. And then, of course, that would be a great way to do it for wells as well. So at this particular site, the DPT injection appeared to be a little bit more successful at the 2-foot, the smaller intervals, for better distribution over the injection wells. But of course, there's economies here. We don't have endless buckets of money from our clients, so we have to be effective in how we choose our technologies. So there are some economies of scale when you're evaluating injection wells versus direct push points. And with that, I'm happy to take any questions that you have, and I do want to recognize Jim Suka from Weston, who's in New Hampshire, and he and I worked on this job for quite a while, and he's been a great resource and help with some of the slides, plus some of all the data that's being provided, so thank you.
Thank you. Good job, Scott. We have some time for questions and answers, and if you have any, please go ahead and enter those now. Okay, it looks like we are getting a few questions. The first one, do you have enough information to determine if HRIT can be used to reduce numerous injections due to rebound?
I would say I don't have enough sites where we've done HRIT to say that site did not rebound. However, I think the data collected from the HRIT is a direct combat to rebound, because I think rebound is I think most of us understand that rebound is many times related to not understanding that contact time, distribution, and where our material is going, coarser grain material versus a finer grain, for example. If you get rebound back diffusion out of finer grain material, these data that we can collect are really analogous to making a better decision at the full scale. So to answer your question, no, but I think the data we have are leading us down that road to make better full-scale design decisions.
Okay, thank you. The next question is, how successful will HRIT be in silty, sand, and saprolite formations?
Silty sand, I'll start with the saprolite. I don't think HRIT is a technology that is made for a saprolite type situation. I think the HRIT is more for alluvium and non-consolidated materials. I think there's probably other technologies that we could use to evaluate those consolidated materials like saprolite. And I think you said silty sand at the very beginning. That's very similar to what we were doing at Little Rock. And so I think one of the great things about it is the ability we can adjust that screen. If you remember at this site we were doing 2-foot injection intervals in the direct push. We can make that a 5-foot screen, a 1-foot screen. So if we do have a lot of heterogeneity in the vertical, we can really dial in what's going to be possible across even very minute changes to the lithology.
Okay, thank you. The next question is the HRIT used to inject permanganate or to inject clean water?
Yeah, great question. At this particular site, we used it to inject clean water. And so it's really a design, its initial use has been as a design tool. I think the capabilities of it, of the componentry, are completely capable of using some type of reagent, although this particular project was just used as a design tool with water. Like I said on my last slide, some of the other things you could do would be reagents, some type of tracer dye in order to evaluate the distribution that you're getting.
Okay. And can you discuss what measures you use to prevent daylighting of permanganate during injection?
Sure. At this particular site, you can decrease flow rate. This is all sites. This is not just in particular this site, but many times injection surfacing happens from old borings, so you can aggressively abandon other borings that happen to be nearby. Many of us have these large sites where they've really put a lot of borings in over the years, and so you start injecting and you start getting surfacing from that route. One way that we have done it at other sites, and this one included, is manifold to different points and decrease flow rate at each one. So you're still getting your efficiency and productivity on a daily basis is still roughly the same, but you can increase a number of points at a time to keep flows and pressures down, which sometimes is one of the reasons you'll get surfacing.
Okay, and next question. During field implementation in the source area, you were injecting into 5+ direct push locations at one time with 210 gallons per location. That is 42 gallons per 2-foot interval. What method did you use to pull up the rods at the number of direct push locations each 6 minutes, on average with 7 GPM flow?
Yeah, no, great question. And that's really getting into the details of operations. And we thought about that, and that's the kind of stuff we think about when we're doing these type of designs. For this particular project, it's not all happening at the same time, if you will. You are injecting it into 5 points, but our field operators, there's kind of 2 ways to do it. At this particular site, we only had 1 direct push rig. One way to combat that would be to have 2 direct push rigs, 1 pushing, 1 pulling. But if you can imagine that you are pushing onto or injecting into 5 points at the same time, however, it's sequential. And so you install your first point, get it at depth, you start injecting. By the time you reach your X number of gallons at that interval, your injection operator or your DPT operator has gotten the next point in. And this kind of continues down the road until you have all 5 in at the same point. And really it just becomes a kind of a dance between your injection and mixing operator and your direct push operator to come back and move around kind of in a cycle. So as they're pushing down the injection tool, they can move back to the first one, push it down 2 more feet. And it becomes an efficiency that we've gotten good at just doing it so many times. If it becomes too fast or your volumes are too low per interval, what you have to do is ramp up to a second direct push rig to really manage it.
Okay. Okay, Scott, have you been able to design an injection grid into clay?
An injection grid into clay? I'm not sure if that's an HRIT tool question or not, but I have not. This is the biggest project I've worked on with the HRIT tool into this non-clay. I have done many, many injection grids into clay with other reagents, permanganate included, and so I've done many designs that way. And if the question is really, is that successful, I'm not sure. I think grid is a very common way of doing injection, but you also have to think about plug flow versus fracture flow, and you know, I typically will have much tighter spacing on a clay type grid because your ROIs are, you know, typically in a fatter clay probably going to be more like, you know, maybe 3 feet, maybe 2.5 feet, which adds, you know, some economies of scale and price when you start talking about that many points. But I do believe that that's probably what's happening in these tighter formations for distribution. Okay.
The next question is, what scope items are included in the $30,000 cost for HRIT in the example case study?
Sure, that included about 3 days in the field, plus an injection rig, or, you know, plus the HRIT tool, plus I think we had maybe 4 technicians out there kind of managing that system, plus the direct push tool, plus mobilization.
Okay. We have a few more. What type of bench tests do you need to perform to on-sites with PCE and TCE? And how long does sodium permanganate last?
I will bench test. You know, I don't want to. I'm a geologist. I'm not a chemist by any means, but I've done a fair number of permanganate injections, and so, you know, we've run P&OD with Karis's labs, and so I don't want to get or speak out of turn from a chemist or Pamela on the line here. But they obviously run P&OD analyses for particular sites, for the groundwater, for the soil, so that we understand demand that's out there for other organics other than what's going to be driven by contaminants. And then persistence, again, I don't want to get in a chemist's way of giving that answer, but I've seen many, many sites where permanganate is still purple and active, you know, 6+ months after injection. I think there's a lot of drivers to that, including, you know, how much oxygen demand there is, groundwater flow, that can really drive how long permanganate lasts.
Okay. You mentioned potentially mobilizing contaminants due to volume injected during full-scale implementation. Was there any concern of potentially mobilizing contaminants during the HRIT phase?
It wasn't discussed, and we're doing such a low volume per point. You know, it was, I think some of the mounding or some of the mobilization, if that's what happened, came from the fact that we did 114 injection points on that south side. When we're doing the HRIT, high resolution injection tool analysis or injection, that was, you know, 8 points. Like I mentioned, I really wish we had done it at perhaps, you know, 20 or 25 points to be a little bit more dynamic across the site. However, even at that small of a volume per point, no, that wasn't a consideration.
Okay. And what is the time frame to complete the HRIT testing for each DPT interval, average assuming it varies with lithology?
It does, yeah, that's correct. It does vary with lithology, and I'm not sure if the question is regarding like the back-end data analysis. You're getting those data in real time. Those are spitting out on-site so you can see it. You know, of course, we did some data analysis back at the office for a while after we kind of synthesized all the data, but you're getting that printout or reading in real time.
Okay. What method would you suggest instead of HRIT for saprolite?
The saprolite, East Coast questioner here. If the question is to evaluate distribution, I think there's tilt meters. There's other ways to evaluate distribution and where fractures are going, because I don't think you're going to get material injected into a saprolite in the way we're talking about here. It's going to be emplaced, it's going to be fractured in, and so really we need to consider where does the material go, and how big are the radii of influence, and that's where tilt meters can be used. You could do certain sonic methods if it kept a core consolidated enough where you'd actually be able to see fractures, or people are putting iron in fractures, which can then be shown. So I hope that answers the question, but I think saprolite will always have to be fractured based on we don't have any saprolite in Colorado, so I believe I have an understanding of its makeup.
Okay. A few more questions here. When injecting using direct push equipment, do you use a mill slot or similar tooling, or inject out the bottom of the probe rods only?
Yeah, great question. And we very, very rarely will do that would be what I would consider bottom-up technology, or bottom-up injection, where you just do a drop point off the bottom of your tool. And the reason that we don't do that is as you get to depth, let's say you go to 25 feet, and you drop that point off and you start injecting, and you pull up 5 feet. So now you're injecting from 20 to 25 feet. If you then create a pathway, or even a small preferential pathway in plug flow, as you pull up to the next interval, now you pulled up another 5 feet, you've now got this huge open space beneath you. I never felt like distribution was as good with the bottom-up technology, just because I never trusted that it wasn't just going into that bottom interval into which I was originally injecting during sort of the first interval. And so, yeah, we use many, many different types of tooling, including what we call like a fixed open tool, which has an internal screen to prevent clogging. And we typically do that with top-down injection strategy, so 15 to 20, 20 to 25, et cetera.
Okay. Can the HRIT be combined with the injection so that you can use it during a pilot test to cut down on costs?
I think that would be a great way. I think that gets back to a little bit to can you inject reagent through it? And I think that's completely possible. But the great thing about the HRIT tool is that it's mobile. I mean, it literally is a pump on a skid with a water tank. We built it so that it was very easily deployed, and so having it sit out there during a pilot scale, I think, is a great idea. You could either do troubleshooting as you're injecting during the pilot scale with a reagent, or you could do it pre-injection at the pilot scale right in the area in which you're going to be working.
All right, and if no one else has any more questions, it looks like that wraps it up. Oh, we got one more. What is the purpose of the downhole pressure measurement? It seemed from the slides like you were looking at the uphole pressure.
We were. For the slides I presented today, we were looking at the uphole pressure. But one thing you can imagine, think about flow through a pipe or a hose like that. You have line loss. And so what we do for many of our sites is we do measure downhole pressure. And so you can then, because your pressure at your pump is X PSI, and downhole it's X, plus something. And that's because there's a little bit of line loss there. And so that's a way to evaluate the line losses. These lines were so short there was very little line loss, but if you have whether it be high resolution injection tool or when you're doing a full scale injection, if you have very long runs of injection line and hose, that will be where you want to consider what your injection subcontractor is telling you the pressure is at their pump versus what is at the injection point, because there will be some differences there. And that's also something for regulators I deal with regularly, because they see a pressure at your pump that you're injecting at, but there's probably a chance that your pressure in situ is significantly lower than that due to line loss.
Okay, thank you, Scott. I think that wraps up the questions. If anyone has any further questions, please feel free to email us. Thank you for your time today.